Okay, let's get started. We'll start this comment. I think it's better to run bigger. So, in Chinese, so TA is the Chinese subject words of these two are TA. So TA is Newton. And then 西方讲 so these two are the TA. Can you create a recent group of this? So, and my office is the Taiwan. Sorry. Uri.
面对面进去3208。
So what's the distribution? You should write it down. So which group? And then please use your in this WeChat group you should use your real name. Use real name. Okay. So that's the information of this lecture. Okay, so about 140 people registered this course, and we'll see how many survive till the end of the lecture. Anyway, so so grading scheme is the 5 tenths of homework. Tenths of homework. Sorry. Okay. Yes. And also, so this is 50%. So this is a grading scheme. So yeah, and then final and the function. Oh my goodness. Okay, so the final期末考试. So these are grading scheme. So those are the grading scheme, and then so this majority 100 students from undergrad and 40 students from graduate students on third semester. And then yeah, of course, some of the graduate students just transfer credit. So I mean, I'm pretty sure like 140 people more. But anyway, so we'll see how it goes. I'm not gonna So this is the first time to teach this class for me. So I think I will make a lot of mistakes and so on. If you think what I said is wrong, or if I tell something wrong, just please tell me, please point me out. And feel free to interrupt me anytime, any question. Yeah. And then for questions, you can ask question via WeChat or after lecture is okay. Also, if you want to, I mean, we can meet in person by just scheduling. Or you can come to my office. That's also okay. So that's and I'm not going to be so fast this time. So I think here people have a different background, different age. So I think it's better to like somehow cover some middle average target average level of the student. So that's the fun of this lesson. So what's the high goal? Even for me, this is kind of my the challenge because this is the first time to teach, and also, yeah, it's slightly different from my expertise. But for me, it's fun to like keep learning the different topics and just convey what I have learned to you guys. So the match. So the idea. And then I think does anyone already have a link to overleaf lecture notes? The lecture note is can you send the link of overleaf to the WeChat group? So lecture notes will be updated. Overleaf. And then what's the so I keep updating throughout the course. So throughout the course, so please always refer to the latest lecture notes. Like every day, I mean, like half an hour before, I keep updating the lecture notes. So please take a look at the latest overlay part. So that's the case. And then textbook is kind of so I found two textbooks. Yeah. So one is the so I mainly refer is the statistical. So statistical mechanics. And then the other is the Coleman. So Coleman, what's the title? Yeah. Coleman, Introduction to Anybody? Anybody? Those are two main textbooks. Textbook. Okay, maybe the textbook. This I can write down I can only write down like all time. And another thing is the is contact. So contact. Physics and mathematics.
对呀，理工平其他又不怎么变。
Okay. I think this is correct. Sorry. This is this one. Sorry. Yeah, sorry. You should correct me. Anyway, so that's okay. So that's the information of the textbook. So those are information. Any question about this course? Any question about this? So the main content of this lecture is first we review. Review, or some of them are for review, some of them are just crash course or crash course. Or I mean. So that's the first part. Number two is the something called the theory of superconductivity. So that's the once we finish this review of the statistical mechanics, we will move on to the theory of the superconductivity. So this is called something called BCS theory. Okay, so that's the first goal of this lecture. And right after that, we will move to the something called the quantum spin system. Okay, so that's the. In particular, we will treat as like a Heisenberg spin chain, Heisen 1D, quantum 1D, 1D quantum Heisenberg chain. And also AKLT model. Those are the main targets of the second half of the lecture. We'll see how the course will go, how much I can cover. I'm not sure how much we can cover, but if time permits, yeah, I would also talk about a lot about this one. So this one, the first one is the something. Okay. That's the plan of the main plan of the this lecture. So, any questions of this? Okay, how many of you have taken the statistical mechanics one? Oh, that many. Okay, many of them have already taken that. Okay, so then I can be very brief. The first one, maybe. I think I can be very brief about the first one. Yeah. Okay, but who is one? Okay. So let's do the introduction. So many of you already know about the canonical, microcanonical, ensemble, ground canonical, and also like ideal Bose cycle condensate and so on. Many of you already learned. Okay, so then I don't. Okay, but I'll have to briefly review those brief. Okay, so what is the superconductivity? So So the beginning of the 20th century is honest. Found that something very, very remarkable thing. So resistance, temperature. So if you look at the mercury of the resistance and the temperature, usually if the temperature is high, electrical resistance is very high. So, but if you cool down the material, usually the resistance becomes small. So because in material there is something like a lattice atom just moving very strongly. And then when you put the voltage, electron move around. Electron move around like this way, and it hits the lattice atoms, so that it just creates a resistance. So if this movement of lattice is big, resistance bigger. So therefore, resistance become like this. But what honest found is that for mercury around the 4 Kelvin, or under 4.2 Kelvin, very low temperature, suddenly resistance becomes zero. Becomes suddenly zero. And then so 0 to 4 Kelvin, so the mercury resistance, electrical resistance becomes zero. So that's the birth of the superconductivity. And the mid 19th century, so Badin, Cooper, Schulhoff, so this is 1957. So they somehow propose the theory behind superconductivity. So that's now is called the theory, and then which is something like alpha. So, for this kind of material, if the temperature low enough, electron forms so-called permanency. So because of Pauli exclusion principle, so the fermion cannot take the same state. So therefore, so you start with the zero energy state, and then the next fermion will take the next excited state, and so they form so-called fermi, like a sphere like this. So this can be understood as a momentum. Okay. So since the and then, so at a low temperature, so they form so-called ball. Their states form the ball, and then the surface of this ball is called permanency. Okay, permanency. So that's usually what is believed to happen. But however, so unlike bosons, so these states has a non-trivial energy. So the bottom can, of course, in bottom, you can always have the ground state. This is the energy. Ground state is the just all state is at a zero energy. But for fermion, you have to have the only each state can have accommodate only one electron. So you behave like the state becomes like this. It becomes like this. So therefore, around the surface of this ball, permeate C, electron has a really non-trivial energy. And then in fact, you can perform one so this is the what Cooper found is that the Cooper. Yes, BCSC is the Cooper. So if you excited electrons have attractive force together, so attraction. I think it's better to write bigger because it's people sitting behind. So electrons are really excited, and then but if you have attractive force, or maybe attraction. So then E minus and E minus. In fact, this state is more total energy of this state is lower than the individual electron at the Fermi. So therefore, if you have an attraction between two electron pairs, so energetically, that's more preferable. It becomes preferable. That's what Cooper found. So therefore, it's for Cooper pair. So they form so-called Cooper pair with bound by the so-called attraction, and then around the Fermi sea, they start creating these Cooper pairs, and then they become energetically more stable configuration. Then what's going to happen is that they in the superconductivity material, what's going to happen at top? So you have a lattice material, and it's point of it has a lattice. You have the nucleon or proton. You can tell. And at the low temperature, and if you put the electron here, somehow this lattice the proton, say the proton, is attracted. So this is attracted. They become a very small, this square becomes tinier. So smaller becomes. So this is attracted by proton is attracted in the middle to the electron like this way, and they form smaller square. Then around here, in total, charges become positive. Okay. Then another electron will be attracted this total energy, positive total energy, to like this way. Okay. Then somehow they form so-called, this kind of attraction will happen so that they form the Cooper pair. So they are bounded them together, and then that would create so-called and they form like a bosonic state. So they form like a Cooper pair with some minus Cooper pair. So Cooper pair, they form Cooper pair, and then form like a bosonic like state. And then what really happened at the superconductivity is that really this Cooper pair just show the both Einstein comments. But so that's what we have. And then show the resistance becomes D. So that's what we. And in superconductivity, because of this Cooper pair, for instance, if you have a material, and then if you put the magnetic field, usually magnetic field will penetrate material. So when T is the critical temperature. But so this is critical temperature. But once the both Einstein condensation occurs, it starts creating energy preferable state. So this Cooper pair just creates some internal like small current, so that they counter the magnetic field B. And then so magnetic field cannot enter the material. They somehow create a small electric current to cancel this Cooper pair, to cancel this magnetic field inside the material. So that is called micron effect. This is for micron. So this kind of stuff is very useful even for daily life. For instance, in Shanghai, there's a maglev train to go to the airport. And this maglev train is really use this superconductivity to achieve this whatever 300 kilometers per hour or something like that. So that's the what happens in the very schematic way of explaining what the superconductivity or detailed theory explaining superconductivity. Let me show something. Okay. Did I? Did it? Oh.
Temperatures. As an electron moves through a conductor, it is repelled from other electrons due to neutral negative charge, but it also attracts the positive ions that make up the rigid lattice of the metal. This attraction distorts the ion lattice, moving the ions slightly towards the electron, increasing the positive charge density of the lattice in the vicinity. This positive charge density attracts other electrons. At long distances, this attraction between electrons due to the displaced ions can overcome the electrons' repulsion and cause them to join. Two electrons, when joined together in this way, are called a Cooper pair. And the positively charged region of the atomic lattice is part of what is called a phonon. A collective motion of multiple ions with the same frequency are called phonons. Phonons are important for conducting heat and sound through solids, but for our purposes, they are important in understanding superconductivity. If the temperature of the material is low enough, the Cooper pair remains together because it does not have enough energy to break apart. This pair can then be treated as a single particle. When two electrons come together in this way, their half spins interact in such a way that together they form an integer spin. In other words, they start behaving like bosons instead of fermions. They are no longer subject to the Pauli exclusion principle. What happens now is that since an arbitrary many bosons can fit into the same low energy state, the collection of Cooper pairs starts acting like one entity or unit. This state, when a bunch of bosons, cooled to low temperatures occupy the lowest quantum room state is called a Bose-Einstein condensate. They act like one bosonic electron, all at the same low energy state. And it's negatively charged because it is made up of electrons that are negatively charged. So this means it can conduct electricity. Normally, when an electron collides with an atom and scatters, it loses some energy by going to a lower energy state than before it collided. This energy is lost to the lattice of the metal. But with Cooper pairs, there's no lower energy state for it to go to. There is no quantum state that these bosons can occupy that is lower because they are already at their lowest energy state. So no energy is lost because they can't lose any more energy. The lack of interaction of the Cooper pairs with the atoms effectively results in no resistance to the flow of electrons, and the material becomes a superconductor. The interaction of the electrons in a Cooper pairing is very weak, so it typically only happens at very low temperatures. As the temperature gets above the critical temperature, Cooper pairs get disrupted because there's enough energy to break them up. And so superconductivity is lost. It's the formation of Cooper pairs to the...
Okay. So this is an animation of what I try to explain a heuristic of it. So anyway. Okay, so those are the theory of the superconductivity, and then there's a high temperature superconductivity was found in the late 20th. So I don't think I have time to talk about this one. But anyway, so those are the schematic, very heuristic way of explaining superconductivity. But through so we'll walk through this BCS theory very carefully by using the physics and mathematics. So that's the one plan of the one of the main goal of this lecture. Any questions, please? Okay. Another thing is that the so another thing is the quantum spin system. Quantum spin systems. So you consider some periodic spin chain, 1D spin chain, like this way, and each side. So there is an L side in a periodic spin chain, and you have the spin variables, spin 1, spin 2, spin 3, and so on. And then if you have a Hamiltonian, Hamiltonian can be written like this one. And then okay. So if you have a minus sign here, they prefer to have the same spin, Okay, so the same spin. Because if you have a same spin, this inner product becomes 1. And if you have a minus sign, it has to be lowest ground state. Okay. But if you have opposite sign, it becomes minus 1. Minus 1 plus minus 1 is plus 1. So that way it becomes excited. So this is ferromagnetic. However, if you have plus sign here, the same thing. So this is called, then they prefer to have the opposite spin next to each other. The spin next wants to have the opposite. So this is called anti-ferromagnetic. Okay, so that's what really happened. Like this one. Okay. And then this S can be whatever. This S spin can have the one half, one, and then spin half. It can have the half integer or strict positive integer. Strict integer. Okay, so that's so this is quantum Heisenberg spin check. This is Heisenberg spin check. It's called spin check. Okay. And then 1983, something today. So 1983, conjecture as follows. So this system has so the how I mentioned that either like a strict positive integer or a strict half integer, it show the totally different behavior in the system. The system show the so this Heisenberg spin chain has a very different characteristic. So for what should I say? Half integer spin. Okay. So for example, in this case, it has the unique ground state, gapless ground state. So it has a unique gapless ground state. So which means that if you have a ground state energy, you have a ground state, but there's a continuum of the excited state. So to go to the next, there's the next excited state. It can go like a very, very easy. Gapless means the energy gap between the first excited states and then ground state is really like bounded by very small, sufficiently small number. So the gapless, so this is important. Gapless. For strict integer, however, integer in case, so they have unique gapped boundary. Gapped ground state. So gap means that there exists some gap between first ground state and first excited state. So you have a ground state. Here you have the spectrum is continuous. However, so for gap to ground state is the ground state here, but first excited state is up there's a gap between like this. So this is called a gap ground state. So that's the 1983 how they made a prediction, and because of this around that time. So this prediction is totally unbelievable. So that actually 1981, Arden wrote some very brief paper on this Arden condition, but this paper is rejected because nobody believes this is true. Actually, 1981 rejected 3 times actually, 3 times. and then it was untouched. So this was really both condition. So both conditions are that time. And then later, so-called so the Harding in 2016, Harding will get the Nobel Prize because, but Harding will receive the Nobel Prize due to this condition mainly. So this is a really bold condition, and then after that, people start looking at the seriously of this condition, and then many things are interesting phenomena happen. So one of them is called AKLP. Oh, sorry. I think very interesting happened between something. So I think as you may have heard of it, eventually this will lead you to some many things happen actually. Many interesting phenomena. So-called AKLP model. And then LS theory. And the so-called symmetry. Eventually, this will lead you to so-called symmetry protection. Protected. Also, so-called SPT. The notion. So this is the 1989, I forgot, something like that. And then chemical project proposal SPT phases come from 2009. So Gush went, and then Holman was Chicago. So eventually, it is very important the study of other formula. So that's I wanted to explain a little bit. I can say so let's look at that very briefly. Right. So let's consider spin 1 s equal to 1. So s equal to 1. Heisenberg spin. Heisenberg s is 1. Then Sx is given by 0, 1, 1, 0, 0, 0. So like this way. And after and then Fy is the curve 2 is a 3 by 3 matrix. I mean, as you know already, you have the two spin how to say? So if you have a two spin 1 half pi of spin 1 state and spin trivial state, so the 3 has the base is this one. So it has for spin 1 you have a 3 bases for the state. So therefore it has to have a 3 by 3 matrix. Okay. And then you have the configuration one must have the following point. This way, and then SD. Start with 3, 1, 0, minus 1. Like that. Okay. It's not the case. So then, if you apply SD, so I call it this one is the sorry. I call it like this, the 3-stage, like this. And then if you look at so these 3 states of the eigenstate, because it's SD is diagonal, so SD acts on plus, minus is given by plus minus. Like this way, SD acts on 0 here. That's how it behaves under the action of it. And how does spin change anti-magnetic? Sorry, I think I have to mention that you have to use this Hamiltonian. So this Hamiltonian to get the unique ground state. So this Hamiltonian. It expects to have a unique gap to ground state. There are now many evidence for this, which one of them is during the course I will show. But you can consider the trivial unique ground state. H trivial Hamiltonian. You can have this is as J of B. J equal to 1 to 1 to L, so like this one. So we can have this kind of so the Heisenberg spin chain is adjacent spin bar. But this trivial Hamiltonian is just it's just each time you have each time you have the spin z square. You have a spin z square. This is a trivial Hamiltonian. Because what is the ground state of this Hamiltonian? Huh? If you look at this one, it's square because if you do square means that if you have the plus minus, you have that it contributes the h to 1, each side will contribute. But if you put it 0, it just contributes to 0. So therefore, ground state is the ground state is like this. This is a ground state. Okay, the energy is very trivial. And the first excited state is it's just first excited state is you just have somewhere in the plus or minus. So this is the first excited. Excited state. So that's the trivial Hamiltonian. And then the interface can happen. Okay. So therefore, this trivial Hamiltonian has a unique ground state, and then it's a gapped one because this Hamiltonian has energy. This has energy equal to 0, and this is equal to 1. Okay, this is ground state. And this is first excited state. So there's a gap between 0 and 1. So therefore, it's called so this trivial Hamiltonian and the gapped ground state. Unique gapped state. It's very similar to integer, I would say, Heisenberg spin is expected to have. Okay. And people just consider the following Hamiltonian. So the interpolating one is um, this is the trivial Hamiltonian. So this has the interpolate the Heisenberg Hamiltonian and the trivial Hamiltonian. So you can interpolate the S runs from both. So when S is equal to 0, it becomes trivial Hamiltonian. And the S is equal to 1, it becomes Heisenberg Hamiltonian. Those are interpolating one. And then it turns out that if you look at the so this is E first excited state minus E ground state. So we know that this trivial Hamiltonian has the 1. The difference between ground state and the first excited has the 1 energy gap. Energy gap is 1. And how then this Heisenberg spin change, actually it's a numerical check, and it's always it's now believed to be true, and Howden gap. Between first excited state and then ground state. And this Hamiltonian, in fact, has the following the numerical simulation. If you do the numerical equation, become like this. And if you just increase the number of sides, now this number of sides becomes large. This curve becomes lower and lower. So if you go to infinite limit, it is believed to hit to the 0 point. Okay, so this is, or maybe so here it's believed to have this is there's a gapless. If you have infinite limit. So if you have this kind of the gapless limit, there is some state transition may occur in this model. Okay. So if you have an S here, and here you have an H trivial. And then 1, 0. Heisenberg. And in the middle, something like a phase transition point may occur. And in fact, it's believed to have this gap and critical point. So this is called critical point. The critical point. So this is called so the critical point. And here you have you expect to have phase transition in here. So here you have a trivial phase. And here you have the Howden phase. For precisely or non-trivial. Non-trivial phase. And it has the something, number of the symmetry is spin chain has. For instance, time change flip of this the spin, all the sides you can have the continuous flip of the each side you have a spin and so on. So you can just rotate the 180 degree, whatever. The swap the spin, the Hamiltonian has this kind of symmetry. And also, you can just anyway, so you can just say in the middle from here you can just exchange the spin side. This is also symmetry. And what this symmetry protected topological phase is mentioned is that if you don't, if you consider the space of this, if you try to go from here to here, without breaking symmetry, you are inevitably so there's a saying that if you go from one to the other without breaking symmetry, you are inevitably to hit some critical point, which is a gapless point, and go from a trivial phase to non-trivial phase. And there is a topological invariance. In this case, it's called group topology or GU1. There is something called topological quantity that distinguish this phase and this phase. In fact, in this case, example G is equal to D2, and this is just a plus one. And in fact, here it becomes, in this phase, it's crossed by +1, and then for hardened phase, it's actually belongs to -1. And to go from +1 to -1, you really need to somehow hit the critical point. That is what is called symmetry protected topological phase. So that's the one thing I want to explain in this lecture. Does anyone have questions? So this one, this one is actually very schematic. But to before explain this hydrogen speed chain, there is something called the AKLT, Outlet Kennedy LT. I forgot the L. Leaf and Tasaki, 1970. So these are the total model of the hydrogen spin chain, but they consider it as follows. They consider AKLT model is that the HAKLT is something like a sum of SJ, J plus 1, equal to 1 to L. So in addition to Heisenberg, you need to add the following term. You need to add this point, Hamilton. But to find the ground state of this state is somehow, if you use the so-called, nowadays called matrix product state and so on, it's very, like, you can find the ground state. And it shows up in this unique gap ground state. It's a total model of this hydrogen spin chain. And if you use some just use a linear algebra to find a ground state for this one, and you can show up that this has the unique gap ground state for this artificial Hamiltonian. And then you can show up the same thing. So if you consider the interpolation Hamiltonian F is SHAKLT plus 1 minus S trivial. You can consider this one, and you in fact, you can show up there is something non-trivial. You can see that there's a trivial phase and non-trivial phase, and there's something. If you go from one to the other by just changing S, there's some phase transition. That's using this AKLT, so that I want to show that this is phase transition for this like a quantum pinch. So that's the second half, the plan of the second half of this lecture. I just want to motivate you in this for this lecture. So those were the plan of this lecture. So since the first part is kind of most of you guys for you guys boring, you just review this statistical mechanics. Most of you guys, but I think it's necessary to do that. But however, so in due course, we will have more interesting topic I will cover. So I just want to motivate you at the beginning. Any question at this moment? Okay. Then, okay, I think it's a good time to take a break. So let's take a break. So 10 minutes.
他的能体会到自己发现他那边的话。出来了。
对啊，现在刚退的。
我们学生课呢，我还等着第三个版本进来。
那他不是比例法，应该是作为调整，他是调整之后，他接近还有接近那个，我感觉这个政府应该也一样。一加台，然后还有一个这个点，这边调一个点，然后这个点基本在基本在这个子弹量上，这边然后后面还讲首先我觉得，首先公式考的产品，我觉得都是自己我感觉就是它所有资源都是朝相同方向的，那那个是银行的那个这样的，而银行的一个是都很高，一个是它有相当。但是那个叫我猜是所有资源都方向相同，所以全项的所以那个脑袋的其他许多区域，那确实是，所以但是我觉得就有一个方面了，他这个应该是那个讲会不会讲？对呀，但就是也会不会讲？他下节课应该是要讲这个。 应该是暴力屈原，这个动力不是屈原动力想过的，你用那就是两个自学，两个电子系，会是一个不同。然后一个是它，其中三个是一个三角形，一个是一个是三角形。哦，对，对，为什么是？哦，OK。然后这边看就是三形三对三个，总角度上，哎，你有一种方面，应该是它这个觉得，三种它没有，然后这种所以分别了。
28万，
就是这个就是这个太这个啊，这个不是这个啊，这个好吧，然后不然这个没有，这个当时就可能就是我和死，就是说他懂还是那个钱。你知道我觉得这个量比较被动，第一个，this has over it's essentially 对，比一的人会。今天看然后我就看，而且我要没转过人的问题啊，这个也挺。我都会，反正我不懂，我先放你了。做吗？下节课先对，一般先。
啊。
那个在别人还要打分。我明天就早上1节晚上1节。它是没有考消耗，它是每个。然后另一个是那个白色，那个。这个是老师好的事情。哦，其实是各项第一个前一个咨询增量，后一个咨询增量相乘，然后这个系数发完增量相乘，再乘另一个系数，来考虑各项方向。然后咱们。对。
Yeah, so there are some types of exchange. But essentially, you have like infinite many long chain. Zero is the split left and right.
介绍
接管隔壁的那个大钢盘。
Okay, shall we review? Okay, some of the people come up or for the review of the thermodynamics. Thermodynamics. I mean, this course is somehow thermodynamics and then quantity. So somehow I need to cover this one for first lecture. I'm sorry, it's going to be boring, but I mean, in Russia there's a phrasing called repetition is the mother of learning. So even if you learn, repeat learning is also make you help you your solid understanding. So let's do that. So first of all, the fundamental law. Of thermodynamics. First law is the first law is the internal first law is the internal energy difference U. I call it internal energy U. Is actually heat plus the work. So that's the okay. So I use the d for the state variable, infinite change of state variable, and then here you have a non-state d prime is the non-state variable. So infinite change of non-state variable. So which means that there's a system here, and the internal energy will change as you add heat, and then as you add the heat, the prime and work. You can study. So this is the internal energy, and this is heat, and this is work. That's the first law of the thermodynamics. So D prime is the some external force. So this D prime is not energy. Okay. The second law also so that is the statement is as follows. So the infinitesimal amount of heat is bounded by the so-called change of entropy, and is proportional to the change of entropy, and the proportional constant is the so-called absolute temperature. Okay, heat transfer the system from the reservoir T, and then the entropy will just give you upper bound of the heat which can transfer the external source, heat transfer external source and heat transfer E prime Q is bounded by this temperature T and then the entropy DS, the system entropy DS is bounded by E. And then this equality holds for equilibrium. How do you write that? Equilibrium. When the equality holds. Equality holds. The system is equilibrium. That's the second. So it's really second law is the sometimes called Gaussian inequality. Sometimes this is the second law of the thermodynamics. And then, so S is entropy, and third law is given by, if you take a temperature in a system with 0, entropy equals to 0. That's the third law of thermodynamics. And this is called okay, so that's the fundamental law of the thermodynamics. And in particular, so this third law mentioned that if you go to the temperature 0, it's independent of pressure, system pressure, and also it's pressure or limit equals to 0, and also limit equals to 0 means that the entropy is independent of actually you understand. So S is independent of volume and of temperature at the 0 temperature. So this means that because the entropy is zero. So those are the fundamental laws of the law of the thermodynamics, which is very basic thing for you guys maybe. And then we will derive lots of the equilibrium thermodynamics. We derive lots of equations, so we are familiar with it. First of all, the walk down from external source can be written as a pressure times dV. And so this is the infinite of volts is expressed by pressure and volume change like this. And then if you substitute d prime, so equilibrium state, you can have field equality. So if you use the first law and the second law with equality, it means that the du is PdS minus P dV. Because of this, du is equal to d times q, and then plus d prime w. And then so here, this equality is the second and the law. And then walk down from external source is the E times volume change. So this is E times volume change. So from here, one can show that the ds is equal to 1 over t du plus p over d dv. In thermodynamics, it's important to classify extensive quantity and intensive quantity. I forgot how to say in Chinese. Understand? Yeah. Anyway, so yeah, so U and S and B are all from an extensive. Okay. So extensive one. And then, so the thermal equilibrium condition is that if you have the system have, yeah, so those are extensive quantities. So therefore, if you have a subsystem, system 1, subsystem 1, and subsystem 2, and both are equilibrium, and then this wall, if you just put the system, if you put the wall can transfer the heat, then I think then and then here is 1. It's the function of U1 and the B1. S2 is the function of U2 and B2. I put the U in the overline. I put the U in the overline. Always. That's notation. That's my notation to distinguish U and B. If you write down the black code, it's hard to distinguish U and B. I always put the bar on the U. B I don't put. So extensive quantity means that the total internal energy is U is equal to U1 plus U2. And B is equal to B1 plus B2. That's very obvious. I mean, volume is just common. And also entropy, total entropy is the sum of okay, so those are what extensive quantity means. Very simple. Okay, from there one can show the following. If you change the equilibrium condition to determine the equilibrium condition, we just change the virtually Uj, Dj to Uj plus delta Uj, Bj plus delta Bj. Then so entropy is at the maximum. So entropy is always the maximum, means that the delta F is equal to so yeah. So the entropy is the maximum. Means that if you take a derivative with respect to those internal energy and so on. So now entropy is written in terms of function U and B, so therefore you can take the derivative with respect to U and B. And then del Ui, Uj plus del S del Bj, and then Ui. You fix Bj, sorry. And then del Bj. If you the maximum means that the entropy take the maximum, if you take a first derivative, it becomes just zero. So therefore this will hold. And from here, if you take the derivative of S by U, you get 1 over T. But in total amount do not change. The total U does not change. You just keep U and B as a constant in total energy. So therefore, this will give you that this is equal to 1 over T1 minus 1 over T2. It's the del U1. and plus, if you take the derivative of S by V, you get the P over T. I over Ti, sorry, T1 minus P2, T2 is equal to V1. So that's the one equilibrium condition. So from here, this is equal to 0 means that the T1 plus equal to T2, then P1 is equal to P2. It's very, very natural consequence. You put the both equilibrium and you can transfer the energy. Temperature here should be equal to the temperature here, and then pressure here is equal to pressure here. Otherwise, it's not equilibrium. I mean, otherwise, one is pressure is bigger than the others. I mean, wall is push it back to the equilibrium function. So that's why. Yeah, it's a very basic, but let's do one by one. And then, so we can take the general transformation. So the basic example of the general transformation Lagrangian is the whatever. Lagrangian is whatever x squared minus potential whatever. And to the general transformation is just write down x dot is equal to p, and then Hamiltonian is equal to p times x minus Lagrange. So this is called something called the general transformation. That is called the general transformation. And then, so in here, we will take the general transformation for u. Okay. So this is called free energy. And due course, I will always opposite out of free energy. I call it free energy. It's defined as follows: F is equal to U minus E. So F and U are related by the general transformation. It's very similar to what we have H and L. The relation between H and L, U and H, F are just the general transformation. Okay, from here, dF and this is equal to and plug EU, for instance. Yeah, this one. Plug this guy into over there. What you get is that the minus SET minus P. So, free energy, the change of free energy is given by change of temperature and change of volume. The proportional constant is P pressure and entropy. The same thing here. The change of internal energy is given by change of entropy and then change of volume. So this means that when the system is the temperature is constant and the pressure is constant, when volume change or entropy change, internal energy will change like this. On the other hand, the system has the constant entropy, but they change the total the temperature. You should use the free energy. That's what it to measure the energy. Okay. Okay. Any questions for us? So this is called general transformation. Yeah. So F is a function of T and P. On the other hand, U is a function of the S and P. So that's the and they are related by Legendre transformation. That's you already learned. Okay. So now let's consider the system which has also can interact with the external the system can exchange. So if you have an exchange system, you just consider, and then there's another system, and then there's a particle here. Okay, and if you did if you put them together, somehow they can exchange particles through the wall. If you consider such a system, the particle number will change. That will also change. In that case, you have to modify. You have to modify this one by plus mu and Pn. So this n is the number of particles. So energy will somehow it depends on the number of particles you have in the system. And this mu is called chemical potential. Mu is called chemical potential. So similarly, here the F also will change. Once you change the plus, once you change the system can exchange the number of particles. You need to answer. And again, so you can define so here n like this way. So it has a dependence on number of particles. If you have another dependence, you can have another Legendre transformation. Legendre transformation of the F in terms of this mu and n. So number of particles is so-called, this is called ground potential. Ground potential. I mean, just all of kind of just introduce notation and so on for the people. It's very super easy. Where the mu here is it can be obtained by delta and fix T and B. Yes. So if you do that, the change of this ground potential is really depends on the now chemical potential. Therefore, omega is now function of T and B and change this. And with respect to all those derivatives, you get the S and the P and N and so on with minus. So, okay, so that's all the thermodynamic quantities you will have. Okay. And then, so the physical meaning, is ground potential in terms of Hamilton physical quantity is I mean, this one is the extensive quantity. This one is extensive quantity, but the so if you just scale the volume by lambda, so B is the scalar volume of the system, is the lambda B, then you get the quality behavior. So because of extensiveness, you can have this one. Therefore, you see this property. If you use this property, so one can just take a derivative with respect to v, and then the other fixed v and v, and which is just and then the other v lambda v del lambda is equal to omega. Okay. So you get this one. So from here, you get the ground potential derivative with respect to ground potential with respect to volume is in fact equal to minus v, and this is just u. So therefore, if you try to compute the ground potential on the consistent, you just multiply pressure times volume, and then with negative sign. So that's very simple. Can be expressed in the PhD. Any question at this moment? So far, easy for you guys, I guess. And then now, okay. So this is T. Okay. Okay, suppose this is some thermodynamic construction energy in internal energy. Suppose now, from now on, suppose that system has the internal construction. Let us consider S and T, S and U, entropy and internal energy as a function of E and P. Let's consider this one. E and P. Then ds should be del S del P times ds and del S del B times dt dp. Okay. And also with u, P times del S del B P plus I think I should do that one by one. Del U del P dt plus del U del B and dt. Okay, so that's the difference. And then here, what we need to do is just well, I should do it right. Sorry, just a moment. Yeah. So T del S del P. And then you can apply like this way. And then here next is the I got confused. Well, what I'm doing here? So this du dt is the, how do you get it? Plus, yeah, I got confused, sorry. What should I do?
First, E equals to TDS minus dEd.
Sorry. Am I doing correct thing?
That's fine.
Why there is no dB del S? Sorry. Del B del T minus P dt. That will give you this term. Is this the case? I got confused.
Yes, perhaps the Maxwell equation.
Maxwell equation? Sorry. Yeah, Maxwell equation.
Relation. Maxwell relation.
Maxwell relation. Sorry, I got confused. So this, I think it's so simple, but I somehow stumbled. Sorry, del U del T will give you P del S del T, is it correct? That's right. Okay. And del U del P will give you this one minus P, right? Yeah. Okay, right. That's okay. Okay, fine. Okay, and then the heat capacity. So heat capacity is given by it's d times cube dt, which is given by d times del S del T. So this means that this comes from the what is that? Equilibrium is this second law of the thermodynamics, and if you use this relation, this is del U divided by del T. So that's the heat capacity of the system. Now we take the further derivative. It just acts on here is the del B. In del B, and what you get is for you guys, it's too easy for you guys. So use the Maxwell equation. So del B, T del S del T is equal to del T E del S del B plus B. Okay. So is this okay for you guys? So here is the del U with axial derivative del B. Okay. So this is equal to del U del E del T del T. So it will give you this one. So from here, we can show that the del S del B is equal to del P and del T. Is it okay? I think it's my exercise. I think for you, you guys, my calculation skill is not good. Is the B. How do you get this identity from here? How do you get this identity? So I think this is constant P, right? This is constant P, so this is equal to B, I guess. Okay. Is it okay? Then del T acts on this one. Is it okay? And B and T, right? B and T. T is fixed. Okay, so now for this is T fixed. So del T acts on this one, you get the del S del B, this guy. And this del T acts on B, you get the this one. Okay? Is it okay? And this is equal to 0, so that you get this one. Okay, and substitute this one into this heat capacity, with heat capacity. Yeah, I call it this one, CV. EC, heat capacity, no, heat capacity CV. Then dF is given by dV divided by T, dt, and del P, del T, V, and dt. Okay, what is this? S. It's S. So now I use this here. It's a fixed V, fixed V, and I plug this one into here, and then plug this heat capacity into here. That's what I do. Okay, and then similarly you can write down U in terms of heat capacity and then this quantity. So Du, I mean, it's the same thing we can do here. So what we can do is that the yeah. So here, stupid. So instead, so this one is equal to del T. Okay, so that's another way of writing it. Is du in terms of function T and B. Okay, so that's okay. So that's the function of the entropy of the function as a function of T and B. And if you do this Maxwell relation, what you get is that the dV, del dV, del T, del T, T is equal to T del T, del T. So this is essentially del S per del T and del T for giving this relation. So if you take a derivative with respect to here P and B, you get the T over P or del P del T squared. Okay? Del T squared. So that's what you get. So now for this is an identity. Okay. Right. So this means that the equation of state is not precisely then heat capacity can be worse. So this means what? This means that the heat capacity determined. This means that the heat capacity can be determined by equation of state. Equation of state is the P in terms of energy. So pressure in terms of temperature volume is for equation of state, okay? And that will give you the capacity of by integrating the volume. So this is okay, so that's the mean. And then equation of state is often given by this one. Ideal gas system equation of state. So this is called equation of state. And then for ideal gas, you have the ideal gas. For ideal gas, P is equal to nRT divided by volume. Okay. So this is ideal gas. So this N is for number of moles. And R is the for the gas constant, 8.314 joule per mole and Kelvin. So this is for gas constant. Okay, so this and the T and B are as you know. T and B are doing. So this is the ideal gas equation of state. But if you consider a bit more microscopically, whatever, so this will be modified by Wallace equation. Equation is given by P is nRT divided by E minus NV. Like this. And the A is given by interaction. So this A is given by interaction of point. So A is given by interaction constant determined by between atoms. And then B is determined by final size of gas atom, so the size of atom. So those A and B constants is determined by just describe characteristics of atoms for this gas. So that's it for part of mass equation. So therefore, if you know this one, you can determine heat capacity of the material. Okay. Let's take one example maybe for this ideal gas system. So if you flag where can I do it? Where should I do it? Maybe here. So I use the equation which is given by our boss. Value V is given by fixed temperature T is given by this one T, del P, and B minus P. Okay? And then you use the different plugged up into here, you will get as follows. And this, if it is the ideal gas, this is equal to B. So therefore, for ideal gas, internal energy is a function of only T, not V. That's what I mean. It's independent for the ideal gas. And then, for instance, if you use the different, maybe it's yeah. So plug the ID gap into here. Okay. Then it's really del VB, del V. Okay. Del V T is equal to 0. Okay. So it's heat capacity whose its derivative with respect to volume is equal to 0. Any question at this moment? How to fix the temperature T? Any question at this moment? Is it okay? So far, okay. So this independence of B, independence of B is found by Joule, internal Joule. It only depends on temperature T. Is expand in 1840. Okay, so those are very quick reviews of the thermodynamics. Thermodynamics. Any question at the moment? Let's move on to statistical mechanics. Because I think for you guys too easy. So statistical mechanics. So statistical mechanics is just consider some state, quantum state, and the quantum state V, whatever, and then each can take a very large number of values. And then probability is equal to 1. So this is a probability. Of the quantum mechanical many particle system, and then of the state. So if you assume this condition, and then you just consider, so here, statistical mechanics. Okay. Statistical mechanics. Mechanics. Statistical mechanics, and then for quantum mechanical, many particle system. So statistical mechanics will deal with the quantum mechanical many particle system, and you just consider probability W, and the expectation value of operator O is given by sum of WB and OP. P equals 1. So this is the expectation value. Expectation value. Maybe should I mean just say it's like challenging lesson. Challenging lesson. And also I say standard deviation or fluctuation is given by column. O is given by sum of So that's the standard deviation. I don't know how to say in standard deviation in Chinese. What? Okay. 标准差。Right? Okay. 标准差。Okay. Standard deviation. Okay. Good. And this is equal to like standard deviation. So the operator is a deviation. And this is also called fluctuation. How to say fluctuation in Chinese? Yeah. Okay. Fine. So then, assume that the entropy has the following statistical property. Statistical property of entropy. Property of entropy S. And first, entropy S is a function of the probability. So this is the first assumption. Second, is a extensive quantity. If you have a system, so as we saw in the thermodynamics, you have 1 plus 2. So that's the assumption. And third, so you have two systems, two subsystems. And probability W1, and if you have W2, okay? And total total probability for 1 plus 2. Okay? B1 and B2. B1 is the multiplication, is given by multiplication. It's very W1 is very clear assumption. It's very natural. Because I mean, anyway, so anyway, it's very natural. So probability W1 and probability W2, and in total what's happening is the Z population. That's assumption. A very natural assumption physically. And from there we can derive the statistical meaning of the entropy. Okay, so from here, so 0 is S1 plus 2 plus S1 plus S2, and this is equal to sum over B1 sum over B2. That's 2B. And then sum of B1, WB1, 1, F of WB2. Okay, let's I, and I runs for 1, 2. Okay, so like this. So this means that this is equal to sum of B1 and then sum of B2, W B1, 1, W B2, B, and then F W B1. Okay, so that's what's really happening. So here, what I'm doing for Yeah, so I think I use this part. Some of all the possible probability of one subsystem is equal to 1. So therefore, in this one is independent of the W2 or whatever, either W1 or W2. So therefore, if you sum over multiply this one and sum over either of them, this is just 1. And you can plug that in. And so therefore, you can write it down. So this means that this is equal to 0 means that the FBW should be equal to FP plus FW. Okay? FW. So natural quantity of this for this one is the f of x is just log x. Log x. Like naturally handling is this. Fine. So fine. For precisely, you can have some constant shift, but it's yeah. And for the purpose of the normalization, S is given by minus of half of B, WB, and the log of WB. Minus sign is just convention. It's convention. I mean, if you want, you can. I don't like KB, but I mean, I set the KB, but later I put the KB is equal to 1. KB equal to 1. Both non-constant. Runs the convention. Any questions this moment? So this is the statistical meaning of the entropy. Any questions on this?
I have a question. The S equal to the sum of omega and the function of omega. So why the function only relies on omega?
So that's the assumption.
Ivy has this assumption. It's very strong. 它的叠加是线性的。
Question. Why echo? Entropy depends on the function of the property. I don't have a good answer to this. Yeah. I don't have a good answer. Okay, I'll think about it. I'll think about it. That's a good question. Why it has to be functional property? No, I don't have a good answer on both myself. Okay. I'll think about it. I'll think about it. Okay. So and then so this one is that the so this is the equilibrium. So the assumption equilibrium. The assumption is system is that system is equilibrium. Okay. So distribution of the equilibrium is the characteristic. But as you know, so the S who is the ds is always zero from the taken thermodynamics law. So if you consider that the initial state S T1 and sorry, hold on. And then should be ST2 if the T1 is T2. But to derive this from the microscope way, you have to know about the time dependence of W, which is actually a really difficult problem. So microscopically, so to derive this second law of thermodynamics is not so easy actually, in fact, by using this microscope. That's one remark. Okay. Any other questions? Any other question? I could answer to your question, but I'll think about it. I don't know. I don't have a good Okay. Fine. So now we talk about the microcanonical. I don't. So I have only 20 minutes left. I don't think I can cover everything. But so let me summarize. Many things. So microcanonical, a canonical, and ground canonical. Okay. And then here fixed variable is the energy U and B and N. So the particle is this one. On the other hand, the canonical is temperature P and B and N. So those are the fixed quantity. And then here, so ground canonical is the T and the B and E. So these are fixed quantities. So the difference is that so here energy is fixed, but here temperature is fixed. So the system is some like how to say it's a collective sum of us for canonical sum. So the temperature is constant. So on the other hand, the microcanonical temperature can vary, but the energy don't change. So it's just some isolated system between. So that's the difference. So temperature can change in the isolated system, but in the total energy needs to be energy conservation is happening. Here's it's system connected sum of us. And ground canonical is not particle exchange chemical. So that's the way. Okay. And the energy exchange is no and yes and yes. Because I mean here, U is constant, so which means that you cannot energy. But here it's collected sum of us. So now some of us can give energy or absorb energy, what we should. And here particle number can change, so that will change, give you the energy exchange. That's the thing. And particle exchange. And this is the no, and the yes. Okay, so those are the case. And then probability weight, so WB is the constant. So equal for all states, equal for all states, any state, any P, any equal for any P. And here E to the minus measure, EB. Okay, so that's the weight probability W. And here E to the minus B, EB minus the mu times Ni. I think it's too small for. Small and EB. Like this. Okay. And the partition function here, so the Z, partition function called Z, is that this is omega U and V N. So it only depends on the thermodynamic quantity. Thermodynamic quantity. But here it's just I'm sorry. Okay. Let's change the column. So this is the energy exchange here. So here is the energy exchange. Exchange is the no, yes, and the yes. And then this is partition function B. So the partition function C is the omega U and V and N. So it depends on the thermodynamic quantity, and Z is equal to half of B and E to the minus the letter E. And here Z is equal to sum of E to the minus the letter E minus mu. And so those are the very brief summary of the difference between canonical, like ensemble you use in the statistical system, mechanical system. Okay. Okay. So let me give you a summary of the. I think I should more precisely probability divided by D. Divided by D. Precisely divided by D. This is more. Okay, let's talk about microcanonical ensemble. So fixed volume and a fixed internal energy and a fixed particle number, and then states with identical U is the So we want to maximize the function S scalar with the F minus lambda sum of WB minus 1. So this is the so the Lagrangian multiplier. So this is Lagrangian multiplier. And maximize S scalar. So this is equal to minus sum of B, WB log WB minus lambda and extension. And then to maximize this one is that the WB is equal to 0, where WB is the WB equilibrium. And as a maximum state and a maximum state, then if you do the derivative, you have log WB EQ plus 1 minus lambda. So that's the okay. So that's the probability that maximize this SQ. Maximize this SQ. So therefore, this WB is just e to e minus lambda e minus 1. So it's just e to minus 1 minus lambda. Extend to yeah. So this means that this is constant. So that equal for all states, any state B, to maximize this probability. So therefore, we can just set this one is equal to W. This one is equal to W. In my course, cannot ensemble. So this we have the W of B, BEQ is equal to 1. So therefore, this means that W is equal to 1 over number of states. W is the number of states. Number of states. Okay. And then S EQ is equal to log of W. Or log of W. So this is a canonical microcanonical ensemble of this. So this means that as you first time you learn in the statistical mechanics, log of entropy is log of number of states. Okay. So this means that you are in the microcanonical ensemble. Okay, so any questions at the moment? And then if you use this one, you can just, and W is depends on U and the B and W, right? So del S of del U of fixed B and N, and this is equal to this is how you define temperature. And this del S del P fixed U and N, and this is over T prime. And then del S del N U and fixed B, and this minus mu over T. So once that is known, so that you can define the temperature, pressure, and the mu from using this formula, thermodynamics quantity. Okay. Any question at this moment? So that's so when you said that the entropy is a number of minus log of the number of states, which means that you are in the microcanonical process. The canonical ensemble is the so canonical ensemble is the so here we just maximize the entropy S, but now also we can change the temperature so that the you have to so here microcanonical and canonical is difference is that you can change the temperature. So the now we maximize the free energy. Free energy is translated into the free energy. S and is E, E minus ES plus lambda with W sum of B, WB minus 1. So this is Lagrange as before. And this can be written as sum of B, WB, EB plus E log WB, okay, plus lambda minus lambda, okay, minus lambda. And then we will maximize this free energy with respect to WB. Okay, and this will give you EB plus E, and then log of WB plus 1 plus lambda. So this means that the WB is equal to E to the proportional to minus epsilon B divided by E. I put the K, okay. If you want to, you can restore KB, 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 so therefore you have a KB. It's proportional to like this. So you can derive this one to maximize free energy. So then you can have a partition function is that like this way, then you can after that you can just then plug this one back into here. What you get is that it is FEQ. FEQ plug into here is equal to sum of WB is equal to epsilon B plus KBT minus epsilon B divided by KBT minus log of B. This constant is in fact this constant is log of Z. You can have this way. Here Z is equal to E to the lambda over KB T, and then plus 1. You can just, if you use this relation, you can just show that the Z is equal to E to the KB, E to the over KBT plus 1. And plug that one into here, you get the previous equation. Okay? Previous equation. Okay, so and then this is equal to so since they cancel, so they cancel, so therefore this is equal to minus KB T log of so that's what's really happening. Am I doing correctly? Is it okay? I think it's okay, right? Okay, so that's what we have. Sorry. So how do you derive from here to here? Sum of B WB minus KB T log B. Oh, okay. And since the sum of W is equal to 1, so it's just okay. So that's what you're familiar with. Okay. Okay, once this is known, so we can just derive the thermodynamic quantity as del F del T using this relation minus F del F B minus B del F del N T and B. U is given by del B later. Log B. And the U is given by it's calculated from partition formula. So these are all familiar with, I think you guys are. And in particular, so some other specific heat capacity is just to give you the is the 标准差 of the energy. With dP heat capacity is given by W, del 2, with B and Z. So that is given by 1 over KB T del 2 del beta square log B. Okay, so that's the log B, and this is equal to. So if you use this relation, so if you use the Z is given by like here, and take a second derivative of this one. So then what you get is that the 1 over KBT, and then sum over B E to the minus beta E B in B squared. EB squared, and then the other thing is that the other thing that is minus sum over B E minus beta B and EB with square. That's what you get. So this means that this is E squared minus delta B squared divided by KB. Okay, so that's what you get. So this is the heat capacity is essentially the standard fluctuation, standard deviation of the energy E squared. Okay. I don't think it's a good idea to have the Grand Canal ensemble. Let's stop here. Let's go.
因为我看这路相对大，我还是会讲这个的。两个乱七八糟。